Welcome. In this video we're going to take a look at circular motion and specifically the forces involved in circular motion. The force that causes something to go in a circle is called a centripetal force. And we've already seen that when something is going in a circle, let's just say we have an object here going in a nice little circle and it's got some velocity v, that's the tangential velocity, and it's got some mass m. We've already seen that it has an acceleration called a centripetal acceleration going in towards the center of the circle. And we developed an equation for that centripetal acceleration. It's equal to v squared over r, where again the velocity here is the tangential velocity of this object going around in a circle. And we know also from Newton's second law that if there's an acceleration, there must be a net force. So the net force, which also for this object moving in a circle goes in towards the center of the circle, is called the centripetal force. Not centrifugal force, but centripetal force. It's spelled for you up here at the top. Centrifugal force is a fictitious force. It's a force that we feel as a result of going in a circle, but it's not an actual force. It's a reference frame issue, and we'll talk about that in class. But if we know from Newton's second law that F net is equal to ma, then the centripetal force is just equal to the mass times the centripetal acceleration. So an equation for the centripetal force is mv squared over r, where again that's the tangential velocity. So the question that you need to ask yourself when something is going in a circle is, what is the force that is causing the centripetal force to make this object go in a circle? And that's where you're going to end up with your starting point. We're still dealing with Newton's second law, so we're still looking at the sum of the forces is equal to ma. It's just that in this case, the sum of the forces is equal to m times the centripetal acceleration. Let's take a look at an example of something going in a circle. This is like a tetherball. We have a tetherball swinging around in a circle with some tangential velocity v. So our free body diagram for this guy is we've got mg going down and we have the tension force going up at an angle. Those are the only two forces acting on this ball. So the question is, why does it go in a circle? There must be some force or component of force going in towards the center of the circle that's causing the centripetal acceleration. And in this case, it is the x component of the tensional force. So that tensional force has an x component, it's also got a y component, and we can see that the y component is equal and opposite to the weight force. The x component is what's causing the centripetal force. So the starting point here is the sum of the forces acting is equal to the mass times the acceleration of the ball. The acceleration is a circular acceleration, so a centripetal acceleration. Ty and mg completely cancel each other out, so the net force here is just tension, the x component of tension. That's equal to m times a sub c. So we have an angle theta up here at the top. We can see that tx is opposite that theta, so we have t sine theta here is equal to m, and we can input v squared over r now for a sub c. So from this point, we can solve for lots of stuff. If we know the velocity and the radius of the circle, we can solve for the tension in the string. We also need to know theta. If we know the tension in the string and the velocity and the radius, we can solve for what the angle is going to be. We can solve for the velocity, we can solve for the radius. It just depends on what we know in the equation. But the key is that it is that x component here of the tensional force that is supplying the centripetal force to make this thing go in a circle. In the y side, this might come in some problems. We do know that the sum of the forces in the y direction is 0. And we have ty minus mg is equal to 0. So ty is just equal to mg, which we already knew conceptually. So let's be specific here. The sum of the forces in the x direction is equal to the mass times the acceleration. The ball is accelerating in the x direction because it's going in a circle. All right, so we can't forget that acceleration is change in velocity. Change in velocity can be change in speed or change in direction. In this case, centripetal acceleration is a change in the direction. So we do have an acceleration. Let's look at another example. Here we got a car going around a curve, and we assume that everything is completely flat and horizontal. So the force is acting on the car. We've obviously got the weight of the car going down. We have the normal force from the ground pushing up, and there's a static friction force here for the car. And that static friction force, in this case, is what is keeping the car going in a circle. If the static friction isn't large enough, the car is going to slide out of the turn. So a lot of times what we're concerned with in these problems is how fast can the car go through the curve, how big can V be without the car slipping out. We have a maximum value for the force of static friction, which is given by the coefficient times the normal force. So using that, we can solve for perhaps the maximum velocity. So a free body diagram for the car, if we just draw it as a square here, let's say that this car is coming at us. We're looking at the headlights here. Let's draw in some headlights. There are the headlights of the car. So the free body diagram for the car would be, again, mg going down. We have the normal force going up, and then going in towards the center of the circle, we have a frictional force, F sub s. So the question we ask ourselves is what force supplies the centripetal force to keep the car going in a circle? And the answer is the force of static friction. Without that, the car would not go in a circle at all. It would go straight. So doing our Newton's second law, we've got the sum of the forces in the x direction is equal to ma, and this is a sub c, this acceleration of the car going in a circle. The sum of the forces in the y direction is going to be 0. It's not accelerating up or down. So in the x direction, all we have is fs is equal to ma sub c. Let's just go ahead and say that in towards the center of the circle is positive in the x direction. So fs then would be positive. And in the y direction, we have the normal force minus the weight is equal to 0. So on the x side here, we can input coefficient times the normal force is equal to m, and let's go ahead and put v squared over r. And over here on the y side, the normal force is equal to the weight. So now we can plug in mg for our normal force, and we get our basic equation. The coefficient times mg is equal to mv squared over r. Notice that mass cancels out. The mass of the car doesn't matter. So we just have mu times gravity is equal to v squared over r. And from there, we could solve for all sorts of stuff. If we know v and r, we can find mu. If we know mu and r, we can find v, etc., etc. So that's the basic situation for a car going around a curve. Let's say we've got a coin sitting on a record, and the record is turning around in a circle. You've got friction involved there, keeping the coin going in a circle. All right, so all sorts of fun that we can have with this. Also, you can think about there's a person in the car. What keeps the person in the car going in a circle? What is supplying the centripetal force to keep them going in a circle? And it's really, you could think the seat belt, or the frictional force between the butt and the seat, or the car door pushing in on them. All sorts of things like that. Other examples where we're going to use this, other examples of things going in a circle. You, right now, as you're watching this, are going in a circle. You are on the Earth rotates once every 24 hours. You go in a circle with it. What causes you to go in that circle? Here's the Earth, here's you, it's the force of gravity. Where does it point? In towards the center of the Earth. You go in a circle with the Earth, and the reason you do is because of that force of gravity. Or you're also going in a circle because the Earth is traveling around the Sun once every 365.25 days. So here's the Sun, here's the Earth, here's you on the Earth. The Earth is going around the Sun like this in a great big circle with some tangential velocity. What keeps the Earth going in a circle around the Sun? The force of gravity between the Sun and the Earth. That's supplying the centripetal acceleration to keep the Earth going in a circle. All right? So these are very important types of circles that we're going to deal with in much greater depth. But again, we ask the question, what force, we already know of all these forces, what force is causing the centripetal force to keep the object going in a circle? All right? So when you approach these problems, ask yourself that first question. What force supplies the centripetal force? We're still using Newton's second law. The sum of the forces in the circular direction is going to be m times a sub c. The sum of the forces in the perpendicular direction is usually going to be 0. All right, good luck. See you next time.